Okay guys, we're going to go ahead and get started with our inelastic collision notes. And on this first slide, I just got a GIF for you where you can see this giant truck, the momentum transfer truck, hitting this little tiny red car. And we can see that as this truck moves into this car, the truck is initially moving and the car is at rest, and then they hit each other and they both move together at the end. That's really what an inelastic collision is, and we'll talk a little bit more about it on the next slide. But some key things to notice here is that initially our truck is moving with a velocity of 20 meters per second, car 0. Then when they hit, they're both moving with the same velocity of 15. So let's explore that a little bit further on the next slide. So what happens to the objects after they collide? Well, we saw on the last slide that after they collide, they stick together. And that's what inelastic collisions are. They're collisions where two objects end up sticking together in the end. What happens to the masses of the objects after they collide? Well, if they're stuck together, we can argue that now it's just one giant object. So the masses are added together. And then lastly, will each object have a separate velocity after they collide? Well, we just saw in our last slide when those objects hit each other, if they have combined to make one object where their masses are added together, that means that they're going to have the same velocity. And again, that's because they're stuck together. If two objects are stuck together, they have to have the same velocity because they're both moving at the same rate and they're both moving together. So let's take a look at our first example problem here. And it says two meatballs are speeding directly towards each other. One is a 4 kilogram meatball moving with a velocity of 6 meters per second, and the other has a mass of 2 kilograms and a velocity of -4 meters per second. If they collide inelastically, meaning that they're going to stick together, what will be the velocity of the resulting 6 kilogram meatball immediately after the collision? So first thing we want to do is identify any given information here in our momentum chart. Well, it tells us meatball 1 has a mass of 4 kilograms and meatball 2 has a mass of 2 kilograms. So I'm going to go ahead and write that down here in my table. I'm also just going to add up those total masses, and I figure out that when they're added together, it's 6, which is what it tells me in the problem here, that after they collide with each other, the resulting meatball has a mass of 6 kilograms, which makes sense because if we are having those two meatballs stick together, their masses are just going to add to each other. Next, we're going to go ahead and identify velocity. And it says meatball 1 is 6 meters per second and meatball 2 is -4 meters per second. So go ahead and put that in our momentum chart as well. And then our last step is just to figure out momentum. So momentum is just mass times velocity. Well, for meatball 1, that would be 4 times 6, which just gives us 24. For meatball 2, that's 2 times -4, which gives us -8. Our total momentum is us adding those up. So 24 plus -8, if we add those together, we're going to end up with 16. Now that we have before the collision, let's go ahead and look after the collision. After the collision, it said that the meatballs are stuck together and that they have a mass of 6 kilograms. So I'm going to write that here. You'll notice that now I only have one giant box for mass. And again, that's because my two objects have now become one, so I only need one box after the collision. The velocity though, well, we don't know that right now, so we're going to skip it. What we do know though is that the momentum before is going to be the same as the momentum after. So if we had 16 kilograms times meters per second for our momentum initially, that momentum is going to be transferred to the end, and we're going to end up with 16 kilograms times meters per second of momentum at the end. Now that we know the final momentum and we know the mass, we can go ahead and solve for velocity. To figure that out, we're just going to say momentum divided by mass equals velocity. So 16 divided by 6, that's going to give us 2.67 meters per second. And there's our answer for our first inelastic collision problem. So now let's take a look at explosions. Explosions are really just sticking in reverse. If you were to show me what an explosion looks like with your hands and then put that in reverse, you would see that, hey, I'm starting with one object for an explosion and ending with two. But if I do a quick little reverse on like Snapchat or something, you would see that, hey, I'm starting with two objects and ending with one. So again, an explosion is very similar, and that's why it's also an inelastic collision. It's just the opposite. So let's take a look at our problem. Our problem says a school bus with an initial mass of 10,000 kilograms explodes and breaks apart into two giant pieces with a mass of 7,000 kilograms and 3,000 kilograms. The smaller piece has a velocity of 10 meters per second, and the bigger piece has an unknown velocity. So here's our school bus on the right-hand side. So before we dive into this, let's just think back to what I said. Explosions are like reverse sticking, so they're also going to be inelastic. Now let's take a look at our momentum table below. So before the collision, and by collision we just mean explosion, what's the mass of the school bus? Well, that's 10,000 kilograms. What's the velocity of the school bus? Well, before it explodes, it's just at rest, it's not moving. And this is going to be the case 99% of the time for explosions. So now that we know that the velocity is 0 and the mass is 10,000, well, what's the momentum? Momentum's just mass times velocity. 10,000 times 0, that's just 0. So the initial momentum for an explosion, assuming it's not moving, is always going to be 0. So if we know the momentum before, that means that we're going to know the momentum after. And if it's 0 in the beginning, it's going to be 0 at the end. So now let's identify what the masses are. Well, the bigger piece had a mass of 7,000 kilograms, and the smaller piece had a mass of 3,000 kilograms. So the final velocity of the small piece, it tells us is 10 meters per second. So we can go ahead and put that there. And then to figure out the momentum, well, we just need to multiply the mass times the velocity. So 3,000 times 10, that's going to give us 30,000 for the momentum after the collision for the small piece. Well, we know that the total momentum should equal 0. So what does that mean? If the small piece's momentum is 30,000, the big piece needs to have a momentum of negative 30,000. Because if we add those two together, we'll get 0. Now that we know the big piece's momentum, we can go ahead and solve for velocity by taking the momentum, negative 30,000, and dividing it by 7,000. We find out that the velocity of the big piece should be about negative 4.3 meters per second. This is just telling us that the big piece is moving to the left at a slower velocity, and the small piece is moving to the right with a faster velocity. Let's quickly recap what we just talked about, some important concepts. And the first one is what happens to the objects after they collide? Well, when objects are colliding, they're going to stick together. And if we said what happens to objects after they explode, we're going to end up with more objects than what we started with. In most cases, we'll just have things explode into 2 objects, but we could have things explode into 3, 4, 5. The possibilities are endless. What happens to the masses of the objects after they collide? So mass after we collide is just going to add up. We're going to take all those masses from those objects initially, and when they collide and they stick together, we're just going to add all those masses up to figure out the total mass. On the flip side, we would take that initial mass and it would get separated into all these little pieces if we were to explode. Will each object have a separate velocity after they collide? Well, after they collide, they're stuck together, so they will have the same velocity. And again, on the flip side, for an explosion, they will have different velocities. And that's because they're going to have different masses after they explode. But something else I'd like to talk about real quick is what is the velocity initially before an explosion? Well, 99% of the time, that answer is just going to be 0 because our object's going to be at rest before it explodes.